We are going to work through an example of the single sample t-test, which is a statistical test comparing a mean for a sample drawn from a population with the mean scores for that population in a situation where the standard deviation is unknown. The problem reads, are the well-being scores for people who have just ended yoga, shown below, different from the well-being scores for people in general? Mu equals 60. Use alpha equals 0.05. We begin this problem, as we have done in the past, with step 1, which invites us to parse the problem. Pick out the important information from the problem. Population 1 in this situation is, this is the treatment group that has had something different done to them or who have done something different. And in this case, people who have just ended yoga is the good example. People who have just gotten out of a yoga class. I'll write people after yoga. Population 2 is, of course, that general population, people in general. The dependent variable, or the factor that we're going to compare between these two groups that we think might be different for people after yoga, is well-being scores. The tails, or the direction of the test, is that situation where we're looking to see whether we are expecting our dependent variable well-being to be greater than, higher than, more than, or less than, fewer than, if we're looking for directional words like that, which would indicate a one-tailed test, or we're looking for just a word that says different, which would indicate that we don't know whether it's going to be high or low. And in this case, we can see the word different, which indicates a two-tailed test. And of course, the two tails refer to the tails of the distribution. So we're looking to see whether our sample score is in either tail of the distribution. We will have a significant difference if it is up here or if it is down here. That's what we're looking for. The research hypothesis will indicate as H1, and we'll simply state it really easily right now. I'll say it as I write the symbols. The mean for population 1 will be different from the mean for population 2. And our null hypothesis just neutralizes that. Our null hypothesis will abbreviate as H0. The mean for population 1 will be equal to the mean for population 2. And if we can't reject the null hypothesis, that would just mean that our mean falls anywhere in this white area of our distribution. Now that we have the problem parsed, let's continue and solve it. We have our scores listed here. The first thing we have to do is to describe the comparison distribution. This is step 2. When you're solving your problems, go ahead and write these steps out. And we do this with both a picture and by describing the center, the shape, and the spread. The center of the distribution holds true just as it did with our z-test. It is mu. In this problem, it gives us right away, it says the well-being scores for people in general, mu equals 60. So I can just indicate that mu equals 60. The shape of the distribution, in this case, we're going to need to indicate that this will be a t-distribution. We have to do this because we use a slightly different distribution because we are now estimating the spread because we don't know. So the t-distribution allows that to happen. And so we're using the t-distribution for degrees of freedom equals n minus 1 equals, the n is 4. There are 4 people, 1, 2, 3, 4. They're numbered for us. 4 minus 1 equals 3. So we're going to be looking up the value, the cutoff points based on the t-distribution for degrees of freedom equals 3. And for the spread, we need to look for, in the end, the estimated standard deviation, indicated as S, for the distribution of means. We'll fill this in at the top when we're done calculating it. We will use this left part of the menu to calculate it. And our first step is to just figure out the mean, because we're going to need to compare the mean of our sample with the mean of this population. So let's go ahead and calculate the mean. The mean will be our first calculation. So M equals, the sum of all the sum of all the scores divided by N. We don't use degrees of freedom here or anything like that. We're just calculating the mean, which equals, in turn, if we add 35 plus 50 plus 62 plus 45, we get a total of 192. And N in this case is 4. And calculating that through, we find out that our mean is 48. So next, we have to figure out our sum of squares. Our sum of squares is just equal to the sum of all the deviations squared. Let's do some calculating up here to figure this out. I'm going to add a column for mean and write 48 at each line. We're going to subtract the mean from each of these values. And so let's do that in the next column. In this next column, I'll calculate the deviations x minus m. And in doing so, I find that 35 minus 48 equals negative 13. 50 minus 48 is 2. 62 minus 48 is 14. And 45 minus 48 is negative 3. Those are our deviations. So we take each deviation and square it. And so I'm just going to indicate that we're going to do this asterisk 2, and that means square. That's not an asterisk, excuse me, caret 2 means square. If we square 13, we get 169. If we square 2, we get 4. If we square 14, we get 196. And if we square negative 3, we get 9. Squaring, of course, just means to multiply each number times itself. If we sum all of these, then we're going to sum 169 plus 4 plus 196 plus 9 and square it. And that will bring us to, we have already squared it. And that will bring us to 378. So the sum of squares is 378. The next thing we have to do is figure out the variance, which in this case is going to be the estimated variance. So we're going to use S squared. And again, this means the estimated variance. So S squared is simply sum of squares divided by degrees of freedom, which is equal to sum of squares divided by n minus 1, which is equal to 378 divided by 3, which gives us a variance, an estimated variance for the population. And that equals 378 divided by 3 equals 126. So we know our variance for the distribution of the population is 126. So next we're going to, we don't need to go down and take the square root to get the standard deviation for individuals. We can stop right here. And I'll add, you'll notice this red slash through here. We are now done using the degrees of freedom in terms of any calculations. So you can set it aside. We use it only one time, and that is when calculating the variance. So the next step and the final step is just to make sure we're not comparing apples with oranges. We want to make sure that we're comparing distributions with an n equals 4 with a distribution that has sample sizes drawn of 4. And we do so by calculating the distribution of means. I'll work in blue now so we can see this next step. This is the standard deviation for the distribution of means, which is equal to just the square root of the variance divided by n. And we can run that through. The standard deviation for the distribution of means equals the square root of 126 divided by, and in this case, not degrees of freedom. So we're dividing by 4 equals 31.5, the square root of 31.5, which equals 5.612 486. We'll write it over here for our final usage, and I'll write it simply as, I'll write the whole thing out because we'll need to use it again. 5.612486, we'll use that for any calculations. And if we're going to write it on the chart, we'll just write 5.61. We're done. Almost done with step 2. We just need to clarify up here what this refers to. And what this means is that our standard deviation for the distribution of means, and we'll imagine that this is what this is. The distribution of means and the estimated standard deviation for this distribution is going to be 5.612. So the standardized score will be 0, 1, 2, or thereabouts, -1, -2. And the scores that we'll be comparing it with have mu equals 60. So I'll put 60. And then one standard deviation above would be 65.6. And one standard deviation below would be 44.4. And this is so that we can eventually compare our raw scores and see if this makes sense. So we're making progress. We've calculated the spread. That is by far the biggest step. In step 3, we simply need to determine the cutoff point and determine cutoff. We do this with a website that I've given you, or else you can do it on the chart in the back of your book. And let's go ahead and get the website right now. So this is the t-value critical calculator. Just so you remember, I've talked to you about this. We look for 3 values. Critical value, again, we have been calling that the shaded region and the cutoff point. So the critical value means the same thing as cutoff point. In this case, we're told to use 0.05. And in this case, we have n-1 degrees of freedom, which is 4 minus 1, which is 3. We can now just hit enter or calculate, and we can see that the critical value of t in a right-tailed test, and that just means a one-tailed test looking for values on the high end, is 2.35. And the critical value of t in a two-tailed test is in either side of either tail of the distribution is 3.18. We know we have a two-tailed test, so we need to use this plus or minus 3.18. In this case, the t cutoff for degrees of freedom equal to 3 equals plus or minus 3.18. And that means that our cutoff point in this distribution is going to be at this 3 kind of a level, not at the 2 level. I've got it kind of small up here. So this is going to be 3.18, and this is going to be 3.18. We know that this would be a little bit tighter than I have it drawn here, but my pen doesn't quite get that small. But let me see if I can fill those in a little better. We would have 0, 1, 2, 3, like that, and -1, -2, -3, even that isn't quite far enough. That's okay. I drew it a little small because of the size of my screen here. So we have the cutoff point determined. Our next step is to calculate the standardized value for our sample score. In this case, it's a t value. In the past, we've been calculating the z value. I'm going to just put standardized so we get familiar with that term. And in parentheses, I'll write t-score for sample. So we take the mean for the sample, t equals the mean for the sample minus that population mean divided by the estimated standard deviation for the distribution of means. In this case, this equals our sample's mean that we found was, let's go find that again, way up in the problem here, I guess, 48. So m equals 48, mu equals 60, and we're going to divide by, we're going to do that subtraction and then divide by this big number, 5.61248. And in this case, we run that calculation equals -12 divided by 5.61248. And we discover that our sample score is -2.13. And in this case, we would plot our sample score right on here. And let's do that in green. Our sample score is 2.13, -2.13. And we ask ourselves our two questions. Is it within the shaded area? And is it to the extreme of the cutoff point? The cutoff point was 3.18. Our value was -2.13, and we can say it is not in shaded area, or what was called the critical area in that chart we saw, and not extreme to the extreme of critical value, which is also called the cutoff point. And so in this case, because that score falls in this white area, instead of on either side in that shaded area, we fail to reject the null hypothesis. And we conclude that people who just end yoga do not have well-being scores different from the population in general. And we would write the statistic after it. We'd write T and then in parentheses degrees of freedom. And we'd write the t-score for that sample equals -2.13. And we write NS for not significant and a period. And that is the end of that problem.